Okay. Everyone hear me okay? Awesome. Hi everybody, I'm Vaughan. This session sort of comes around for a couple of reasons. One of the things is, in my current role and my previous role, I've worked with a lot of game developers. And we come across people developing for a wide variety of Microsoft platforms because we have phones and we have laptops and we have desktops. And so we work with a lot of people at game jams where they're building games. A lot of them are using Unity because it's so quick to get something up and running at a game jam. And then they decide that they're going to start porting it, maybe bring it across to Windows Phone or the lower powered devices, much more lower powered than the ones that they've been working on. So what we do is we come across all these scenarios where we have all these performance issues and they're asking us lots of questions. And generally the performance issues are not Windows specific. The performance issues are because they're just doing something that's possibly bad practice and they're not necessarily aware. The other thing is that I've been a Unity user for about 5 years. I used to run a small indie game studio as well. So I personally have banged my head against the wall trying to find out what's wrong, where is all my performance going, why isn't it performing well on this device. So a lot of this stuff, when I talk about it, you might think that it's simple and it's obvious, but trust me, when you have the problem, you don't really realize that the problem relates to what you've done. So in this session, I'm going to cover off a few things, just sort of building projects and a couple of basics around that. I'm going to talk about what I've sort of called navigating the time loop. That's trying to understand what's happening within every frame that's being rendered within your application. And this is completely relevant whether you're building apps or whether you're building games within Unity. And then I'm going to, and during that I'm going to talk a lot about performance. I'm going to talk about other things that can impact performance. And that's generally where the focus of this is going to be. What I won't be covering is, I'm not going to go through how to build a great game. That can't be done in an hour, and I'm not an expert on how to build amazing games. And the other one is just general UWP stuff. There's some other sessions here that are going to be covering that off. So I've sort of pulled some of that out of what I was going to present, simply because there's the bare metals session where you can talk about looking at doing some really low-level UWP stuff, and some other UWP sessions here, which you'll get a whole hour of that conversation. So I was going to talk more about Unity and tuning Unity for your applications. So one of the issues that we have, especially when you start thinking about the UWP, is the device landscape is very diverse. And when we look at the mobile landscape and we talk about fragmentation of operating systems and devices there, a lot of the time they're still talking about low-powered devices that have varying CPU performance, but the screens are generally about the same size. Even if it's between 4 inches and 6 inches, it's still about the same size. But when you start talking about UWP, you could be on a Surface Hub, you could be on, so that's like 80 inches, you could be on a television, on an Xbox, you could be on a laptop, or you could be down to a phone. And so we're no longer comparing different sort of more powerful, less powerful of the same device, we're comparing completely different devices. So you're going to be deploying to each and every one of them. Now, if you want to build the absolute most richest experience for every device, you probably would do them. They'd still be separate applications. But a lot of the applications that are going to come out, especially when you think about HoloLens, you're going to be deploying across multiple devices where you want to create the best experience. Unless you're doing a AAA title, you probably don't have to worry too much about squeezing every ounce of performance. And so when we start talking about performance, what we're really talking about in terms of game development is navigating the time loop or the game loop. Now, a game loop, for those that don't know, generally looks something like this. There's some form of input to the loop, and then you update the game state. Now, this is happening, could be happening a few times a second, it could be happening 100 times a second, 1,000 times a second. And then you update the game loop, and the game updates its state based on its state and the input, and then you render to screen, and you render at the frame rate that you want to render at. Now, this is sort of a massive simplification of what's going on, but as you can imagine, if that update takes too long, your frame rate will start to drop, you'll start impacting the experience of the user. So if anybody's played games where they open them up on their machine and the frame rate just sucks, that's because there's so much happening every frame, it just can't keep up. And there are ways to mitigate the need for things to happen in sync with the rendering of the frames. But at the end of the day, if the world and the simulation of the game, or if you're looking at architecture and trying to move through that architecture or analyze that architecture, the amount that you're doing every frame, the amount of computation you're doing every frame is going to impact that. It's not just the visual complexity. It plays part of it, but there's a lot of other things that can happen. So if we look at the Unity game loop, we have this scenario where there's a few main things that happen in the Unity game loop in that update bit. There's what's called the fixed update. Now, a fixed update happens at a fixed period of time. So you can make it happen every 0.2 seconds. You can make it happen every 0.02 seconds. It can happen, you determine when that happens. It's a fixed time frame. The update component of a Unity game loop is happening every render frame. So every time it renders a frame, that will be invoked. And then there's the late update, which is the same as update. It's just that every object in that world will update, and then every object in that world will have a late update, because sometimes you want things to happen after everything else is updated. So what I'm going to do is just cut across to Unity. So I'll just do a quick overview of what you're looking at for those of you not familiar with Unity. So up here we have the world. This is the thing that we can edit and move things around. Down here we have the game window, and the game window is effectively what the game would look like on the screen. It's currently not running, so there's nothing moving and nothing happening, but you will notice that if I move something in the editor, it immediately reflects what that would look like from the camera's perspective in the game. Over here we have a heap of assets that are sitting in the level, or in the scene as it's called. And then down the bottom, these are all the assets in the project, all the files that we have access to in the project. And on the right-hand side is what's called the inspector. So if I select something in the scene, these are all the properties associated with that object. Now, Unity has this concept, if I click on the main camera, has a concept of components. So on the right-hand side here, we have things like the transform, where it's located in the level. So if I click on this cube, you'll see it automatically selects the cube here, and you'll see the position. As I move the position, that'll update, but I can also click in here and just go 2.5, and it'll just move it to there. So there's some just really basics there. So when you look at the main camera, there's a lot of components, and those components are actually classes. And if we go down the bottom here, I have one called the Fixed Update Comparison Script. So it's a script that I've created. And that script that I've created, if I click here, it'll actually bring it up in the project view to say, hey, here's the file. And if I double click on it, it'll open it in Visual Studio. And it's just a .NET script, or a C# script to be precise. And all this script does, just to sort of demonstrate what's happening, is I have two values, a test value and a fixed test value. And then on the update loop, where this gets called, that gets incremented. And on the fixed update loop, this gets incremented. So if I go across, again, if those of you are not familiar with Unity, as soon as you create a class, if it's a public, accessible variable on the class, it actually will create them and they'll be editable in the UI. So it doesn't work on properties, but you'll be able to now go in and start updating some of those values. But I'm not going to do that. This is just to demonstrate. So if I hit run, you've got two cubes on the screen. One of those cubes, the update cube, is actually set to update on every render frame. So every time a frame renders, it just rotates a little bit. And then the other one, at the fixed update cube, every time there's a fixed update, it will rotate a little bit. And as you can see, the fixed update is having a lot slower than the actual update. Now, within Unity, you can go in and change this with your project. If you go Edit, Project Settings, Time, you'll see here that the fixed time sent is 0.02, and the maximum allowed time is 0.33 seconds. The time scale is 1. So if I change it to 0.2, hit play, it'll actually move even slower. It's sort of hard to see because it's moving so slow. So that's sort of, just the concepts. I want to just talk about that because we're going to be talking about this concept of fixed updates and updates the whole time through this presentation. So I want to sort of get you across that. So I'll just talk about timing. Now, fixed update is really good for things like responding and moving, where the physics and the simulation of the world happen. The reason being is if something's moving at, say, 30 frames a second or 30 times a second, it will actually move. The eye is not that great at necessarily detecting that. Where the eye is really good at detecting poor movement is actually when the cameras pan and things like that, and when things move around within the application or within the world. And that's why, like a lot of film movies are now done when they do those big pan landscapes, they're looking at doing that with really high frame rate rather than 24, but the rest of the movie they'll still do it 24. Because that big pan, you can really start to see it, and it's just amazing what your eye can detect. So the fixed update is good for updating the physics of the world and moving objects around the simulation. And if you want to sort of control how often something will happen a second, maybe you have an expensive operation or a calculation that you don't want to have happening every frame. You don't want to check if it's happening every frame, which could be thousands of times a second. You want to check maybe 50 times a second, which sounds like a lot, but you'll soon learn that it's just not at all. And then your update is your per frame events, per render events. So you might want to change the color of something every frame, or the actual rendering of that object might actually be important to the simulation, possibly. You maybe want to capture input and trigger something to happen. That might not actually take effect until the fixed update, but you want to capture that input as soon as possible, right? Because users get used to the fact that, hang on, it's laggy, but not only is it laggy, my input takes longer to respond, so therefore it's twice as laggy. The latency in seeing a result is even longer. You do not control the number of times this happens a second. You have no control over that, and you shouldn't assume you have control over that. Because to create the best experience, you want the highest frame rate possible, so you shouldn't be controlling the frame rate. But things that happen in the update have a massive impact on frame rate. In fact, everything has an impact on frame rate, but if you're doing something in the actual update method, you're probably going to have the biggest impact on frame rate. Because if you do something in the update that impacts frame rate, that's going to bring the frame rate down, which means you even have less time to do that, which is going to bring the frame rate down. It's sort of a bit of a snowball. So the thing I'm going to do here is just go back, and what I'm going to do is, so when you build a project, you'll notice that, and what I'm going to do is just open up a slightly different project, one with a few more cubes. Don't save. Here we go. So this one has 360 cubes on it, and I've got a thing down the bottom left which will actually show the frame rate. So if I hit play on that, you'll see we're getting about 50 frames a second, and that'll go up and down. And a lot of the stuff that happens in the Unity editor, the frame rate's generally sort of like, it peaks at probably about 50 frames a second. You know, you won't see it go to thousands per second within the Unity editor just because there's so much other stuff coming on, and you don't really need that there here. But when you want to build a project in Unity, you go up to File, Build Settings, and we can build a project. So if you build a Windows Store project, and here we have a heap of levels that we've added, what I'm going to do is I'm going to get rid of all of them, and the only one I'm going to keep is the one that I had just then, which is that one, many cubes. And I'll just hit Build. And then I'll give it a folder to build into. That'll do, select folder. And away it goes. So what this is doing is that level that you just saw, the game will load. It's the only level in the game, so it just loads straight into that level, and it'll start running when it's a project, when it's a Windows application. The thing is Windows Store applications, what happens is the Unity will actually go and build a Visual Studio project, and you can get it to build and run it, but I didn't want to do that because I want to sort of show you what you can do here. So if we go into the folder, here's the Ignite Unity 2015 solution. And when we open that, we'll see, when it opens, a project which is going to be the application that then gets compiled down to a Windows 10 application. So it's just a Windows 10 project sitting within Visual Studio. And you can choose whether you want to build it as a DirectX application or whether you want to build it as a XAML application. Generally, what I've found is that there's no real need for the majority of the things you build to be a DirectX application. And if you build it as a XAML application, you get a few other things that you can do because you're sitting in XAML. You can actually then go and sort of play with the XAML behind and even do some overlays that you might want to do for your own purposes, probably not for the Final Ship project. So here you've got a heap of stuff that's generally just a normal UWP project. And then up here you can see you can build for ARM. So I've actually deployed it to the phone. But one of the things that you'll do, and I'm not just going to build it here because it does take quite a while, and the reason being is now it will compile down to .NET Native. So it'll build the application really quickly. Actually, I'll just build it now. And you'll notice that it'll kick off the building of the application really quickly, and it'll build it, and it goes, hey, I'm ready, and then it goes, cool, now I'm going to compile it down to .NET Native. And that takes a lot of time, but that gives you a massive amount of optimization. And the application will run much, much faster. So you can see here, going through, and pretty much right now we're built, so that would be not as a .NET Native application. And then the next thing it does is build really quickly and prove me wrong. Okay. But generally that's something that like you can get stuck in that late step. What? You're right. So, thank you. So if you go to master, so this is the other thing. There's debug, there's release, and there's master. Generally, I never use release. Master, is internally somewhere within Unity. They must have been working on how do we configure the project. Well, we won't touch the release one. We'll create one called master, and that's just shipped with the final project. So you've got these 3 build targets. So your debug build target's really quick if you want to do some testing. I find if you're doing performance testing, you should never be testing in anything else except master. There's just no point. If you're doing your performance testing, you want to be building a master. So if I go build again, and in fact, I never do anything except in master, so. I'm just going to plug in some power before I forget. And here's the .NET Native stuff. Whoa. So when I said I need to plug in power, it was obviously a little bit more urgent than I thought. Log back in. Come on. But the .NET A stuff does take a long time, but if you're doing absolute performance testing of the final application, you want to do it in the final state. This is taking a while. Okay, while it's taking its time, doing I don't know what, I'll go back to slides. Oh, that's all it needed me to do, because now it's come back. And I have no idea if this is recovered from where it was when it went to sleep, but it does take quite a long time to do the .NET Native compile. It's totally worth it. However, if you want to do some early performance testing, I'm just going to stop this. If you want to do some just early performance testing, especially if you're testing on a specific piece of hardware, because you're sort of testing against the graphics card and graphics card capabilities and those sorts of things, one of my recommendations is actually go straight into your build settings and actually just do PC standalone. Because when you do that, not only will it be quick, you'll sort of be getting the best performance you can get because this is running closest to the metal on the machine. So there's, Windows 10 store apps, generally the performance in them has improved massively over time. But here's a great way when you've got some obvious performance overheads and you want to look at them. This is a great way to look at it. It's also just a good way to just test your app and get it running really quickly because it builds straight out of Unity, so you don't have you're sort of building a project and then compiling the project with Visual Studio. The other thing is that it's just super quick. And so here we can run it full screen at fantastic resolution on the display. And so when it runs, up it pops, and we're getting around about 50 frames a second, full screen, fantastic resolution. And then I'm just going to kill that. And I've got a shortcut to it here. What I'm going to do is I'm going to run it at a lower resolution, full screen. And so you can sort of go through the scenario. So here we're getting much higher frames per second. So if you're doing things based on frames per second in regards to your simulation, you're always going to look at the time elapsed every single time you do an update, but this is just slowly climbing as it's probably getting a bit efficient, and then it sort of drops again. The other thing to bear in mind, though, is I also drop the quality. And what you'll find is, with this laptop I'm using specifically, I start to hit a frame rate reduction when I hit a certain resolution. So pumping all those pixels and drawing over those pixels becomes the bottleneck. Whereas with other machines, you'll end up with the more objects you have on screen is actually where the bottleneck gets hit faster. And so when you look at a laptop, generally it's going to be resolution that's your bottleneck. When you start looking at a phone, and lower power devices, the number of objects on screen might be actually the bigger bottleneck. So the resolution of this phone is actually higher than that screen. And so when you start to think about, okay, well, what does that mean in terms of how can this, surely this won't cope. Well, in terms of rendering, yes, because some of the times it drops some of the features that are in the rendering. Some of the effects you would see here, you wouldn't see on the phone, and your eyes won't pick it up anyway. I know mine wouldn't. But the thing to bear in mind is that if you end up with a lot of objects, the CPU processing part of the phone that takes care of all the physics and it's doing all those calculations, that really starts to slow down. And I could show you some demos on this afterwards. As I said, pumping them onto the phone all the time is a bit slow. But if anyone wants to see sort of the difference between some of the stuff I go through, I'm happy to show you it, because this is a 950 XL, so it's a really powerful phone, sort of 8 cores and water cooled, but still you can start to see, oh wow, phones can't handle that and that sort of stuff. So yeah, it's got more cores than my laptop. But what I'm going to do here is sort of describe the level and what's happening. So there are a heap of cubes. These are all the cubes here. And the cubes have attached to them a script. And that script is called the update rotator. It's the same script that was there before. And if I click on it and just reload this, cool. You'll see that I have some of them rotating with the fixed update and some of them rotating with the normal update method. And they all have a variable that I change. Fixed is true, so defaults to true, and half of them are set to false, half of them are not. But that's sort of not really important. What's important is this rotate method. And I'm going to go through this, and you'll notice, obviously, here's a really stupid thing that's happening here that does nothing. But this is sort of, when you do your update methods, you're going to have a heap of logic. And that logic might have 100 different things that it looks at before it makes a decision. It starts to get really fiddly if you want to create a really fluid experience, but it's always worth it. But that's just to sort of say, hey, you've probably got a heap of code that's accessing something and doing something trivial that doesn't look too bad, and I'm going to explain sort of why some of it is terrible. So here all it does is it says this, as in this object, grab the transform, which is, you know, the scale, the rotation and the position of the object, and rotate it. And here I'm going to rotate it around the up axis, and the next thing I'm going to do is tell it how far to rotate. And I have a rate that's on every object, so I can say rotate faster or slower, but it's just set to whatever the rate is. And the rate is actually multiplied by where it's sitting on the x-axis. So that's why some of them rotate in really fast because they're further away, and some of them rotate really slow because they're closer. And then the space, and by space you can either rotate it in world space, which means it'll rotate it around the 0 axis, or you can rotate it around its own space. So, okay, vector up means vector up from me, not vector up from the origin. And when I was writing this, I'd totally forgotten that, and I was like, why is everything just running away off screen? It was because they were rotating around the world and rotating around themselves. And then the next thing I do is I also then go and I rotate it around the y-axis. So something really basic, okay? And as I said, here's a heap of stuff down here. Now, you'd look at that code and you go, okay, and then eventually, if your methods were written this way, you start to run into some problems and you start to see some massive performance issues. And you would have probably written nearly your entire application when you start to see the performance issues, and you're trying to figure out where's the obvious hole. And that's where the Unity Profiler comes into play. So the Unity Profiler is this beast. Now, just to let you know, if I'm doing Unity development, I usually do it on 2 or 3 screens. And there's an obvious reason for that. If you're using the Profiler, got Visual Studio open, and you're using Unity at the same time, you're going to start to run into problems, productivity issues very quickly if you're having to sort of check, change, swap something over the top, swap something over the top. You want to be able to see it in real time, and Unity's really set up to being able to change variables in real time. That inspector panel, while the app is running, I can go and change those variables. So what I'm going to do is I'm just going to wind up the application in the editor. We'll let it settle because some of that is startup. I'll just hit stop. And so what you can see here, and it's probably hard to read, but I can't make it bigger, so I'm just going to talk through it. You've got rendering, which is the green bit, so that's how much time is being taken up in rendering. And right now we're looking at 33 milliseconds is the the line at the top, the peak. And that is, that'll give you 30 frames a second, which is probably like as small as you want to go. 60 frames a second, around the 16 millisecond mark, is probably the sort of the minimum desirable, because that creates a very, very fluid application. And beyond that, you're sort of trying to probably be a bit more a purist around the quality of the rendering and the fluidity. You've got things like scripts, so the scripts that are running, so the scripts that I've written, the scripts that I've attached to objects, how much time are they consuming just from running? You have physics calculations, how much time is that taking up? And sometimes you'll see physics calculations in there and you've got no physics in your application, so it's good to go hang on what's going on there. Garbage collection, which is important, and we'll get to that. VSync is waiting to render a frame to the screen, because the screen refresh. There's no point rendering a frame before you're ready. You might as well do it every time that you're trying to sort of hit a desired frame rate. And then there's a few others as well. So, I just dragged others off. So what I'm going to do though is just show you quickly what you can do. So you see how there's like a spike, and that's when it's doing some rendering. But if we go here, you'll see that there's a breakdown here of all the different lines and what they mean. But if we go down the bottom, we can see that 57% is that number there of the processing in that frame, which was around about 3 milliseconds, was in the behavior update. So it's something that we're updating. One of the behaviors that we have attached to an object is consuming a lot of time. And so if we open it, we can see that update rotator is actually 49% of the overall performance. And we can see that it gets called a lot of times. So because we have so many objects, we're calling it a lot of time, because we're calling it for every single object, gets called individually. And so we're calling it 360 times, and it's taking 3.29 milliseconds, and then when you add up, across all those, you end up with something that's, it's got a considerable amount of CPU for something that's just rotating the cubes. And so how can we reduce that? Because even if we reduce that by 50%, all of a sudden, those numbers will look very different. We could probably bring it down. Let's say if we could just bring it down to 2 milliseconds. If all of a sudden you're hitting a frame rate issue, and then you can reduce your overall processing by 60%, down to 60%, that's massive, right? So you get, not only do you maybe get it performing much better, or you could do more processing, but you can also reach a whole suite of devices that you probably were way out of their league. So it's sort of thinking about reducing it is also opening up a new market possibly. So we can look at that, and there's a method there called memory hog, just ignore that. And then you'll notice here though that we've got this tiny overhead, which is the FPS reader. So it's only doing a small amount of processing, so it's not necessarily an issue. So what we're going to do is I'm going to step through the code and talk through some of the performance issues in this code. So when you look at it, the vector3.up method is just giving you access to this sort of static vector. It's talking about the up axis. The thing is that every time you call that, there's an overhead, and it's a very small overhead. But if you think about if you're doing web app development when servers were very constrained, even then you probably wouldn't have thought that this was necessarily an issue, right? But when you start talking about sort of things that are taking nanoseconds, and the fact that that's actually going to impact your overall performance because you're calling it so many times per second. You think about those database calls that people were doing like 100 times a request and not caching data. This is a very similar thing. It's just instead of happening in a millisecond conversation, this is happening in a nanosecond conversation. So the first thing you would want to do is sort of pull out that and store it in a local variable, because we're using it twice here. Maybe we'll store it in the class, because you know what? Up never changes. It is static for a reason, but calling it all the time is going to be expensive. The other thing that is quite expensive here is the this.transform.position.x. That is actually probably one of the most obvious things that you don't realize when you start building applications, because you're like, hey, I can rotate it, it'll be the transform, and I'll do all this stuff, and you probably haven't read up on some of the performance issues with this. By calling this.transform, this in this method is actually the component that's attached to the object. And then when you say .transform, it's actually saying this.transform is actually this, the object I belong to's transform. So can you go and grab that for me? Then position is actually trying to get some other information out of that object. And then X, which X is probably the really low cost operation there. The recommendation here is to always store, no matter what object you have, always store the transform for it. Because it will always give you access to that instance of that object. You just don't have to go and find it every single time you go and access it. The other thing is, within that method, you probably want to grab the position at the beginning. So grab the position when you come in, get the copy of the position object, and then start accessing it. Because again, you're not trying to get the position from the transform. So these are sort of general optimization tips, but they make a massive difference, especially if you've got a method that does 100 different things, looking at space and the transform and the rotation and all that sort of stuff. But then at the end of it, you've got 360 of those objects on screen. So you can think about, for architecture, you might have all these objects on screen that make up a building, thousands of objects. And then all of a sudden, they've all got an overhead, which is 1 millisecond. And it's 1,000 objects. Then all of a sudden, you've got something that's got 1 second frame rate. So, 1 frame per second frame rate. So what I have down here is another method, which is a better rotate. And I call it better rotate. So here we grab a few things. So you'll notice that first line says position equals this transform dot position. It's like this transform. Where does that come from? So this transform is from a class called Smart Behavior. Now this is just a class that I've written, a behavior class that I've written that inherits from the default behavior called mono behavior, and it just stores this transform when it's accessed the first time. So when you say, hey, give me the transform, it actually goes and gets it and stores it locally, and then forever in the property, you've got access to the transform. Now, this is not something that comes out of the box. There's many different ways to skin this cat. I just thought I'd give you this example with this bit. There are other things within every behavior that you'll probably go and access quite a lot that are very handy to have in a base class. And you'll figure out what they are. Everybody, it's a bit different. Some people put game behavior there. Some people put some static singleton stuff in there because they just feel that that's an easy way to access it. But here, now every time I create a behavior, I have a behavior, I never use this.transform anywhere. The only thing I use is this transform, all right? So, and that's just giving me access to exactly the same object in a performant way. The first time I access it, it has a small overhead, and then after that, it has, really no overhead at all. Then I say rotate. The vector3.up and the vector3.left are now up and left. I'm storing them within the class. And I could probably even store them statically. So here I've got them, they're not static, they might as well be static. I don't need a copy of them in everything, right? I can just need a copy of them in this class. And then I just rotate. And then space.self I could do the same thing with. I haven't even done it, right? When I was looking through this, I go, yep, that's absolutely performant. You'll notice that when you go through the profiler, even calls to space.self start to add up. And then, but then this code before, which, and here I could have used pos, but here you'll notice that when I get this code's running. And that code, as you can imagine, will always run really, really fast. As fast as you probably thought the other code was running, but actually, no, this runs incredibly fast because it's doing nothing. And I've left it in there for just, to illustrate the point. And so if I go back across to the profiler, and we just go to the deep profiler to give you an example. Now, the deep profiler is not really a good way to profile your app. If you're actually profiling your application, you are impacting the performance, right? There's an overhead with running the profiler. The deep profiler, there is actually a big overhead. And that's because it's capturing just way more information. So I'm just going to wind that up. And you'll start to notice that the graphs look very different. And the reason the graphs look very different is because the profile itself is impacting the performance, okay? So when you're looking at those milliseconds and those nanoseconds, you've got to sort of take it with, the percentages are probably more important than the actual values because the profiler is actually changing the behavior. But if we go across here, the deep profiler, if I go into behavior update, I can see that in update rotator, I can now drill further into that. And so the actual rotate method within that is where the problem lies. And then I go into that and I can actually say, hey, transform.rotate is very expensive, and you would expect it to be expensive. We're actually operating on it. But actually, transform.getPosition was a really expensive thing to do. Not only that, component.getTransform by going this.transform was something that was really expensive in there. And then you get down to the vector get left and get up. You'll notice here they're very small, but once you start going onto different platforms, you start to realize that method calls on an iOS device and an Android device have very different costs associated with them. So anything that can just reduce the number of method calls that's happening with your application in a clean way that you can still maintain it is always worth doing. So this gives you that deep level of understanding, but you don't want to do it all the time, as I said, because it really starts to sort of skew. You sort of want to get your application to a point where you then want to dive deep rather than run it all the time like this. So what I'm going to do now, very quickly, is I'm going to go into the other level that I have rather than go through and assume I've done the optimizations that I wanted to do. Oh, there was another thing. I'll just go back quickly. If we look at all these cubes, when you create a cube or you create just a basic primitive, it often will attach a collider with it, a physics collider with it. And here we've got a box collider, and it may attach a rigid body. And a rigid body means that it can fall with gravity and collide with other things and react in the physics engine. One of the things you want to do is get rid of all of those. And there's an easy way to get rid of them on all these objects. I can just select them all because they're all exactly the same. You'll notice here that they even have the same position, so I can change all of that and change all those values. But I'll just remove that component and I'll remove the rigid body. And that actually gets rid of a heap of physics calculations. So if we actually were to look at what the profile I had before, there would have actually been, if I scroll down, we can look at physics. You see how there's lots of lines there in the physics? There's lots of physics stuff going on, but there's actually no physics interaction going on. We're just rotating things. We're not colliding things. So it's another thing. You go and create your whole application. You create everything. You've got all these colliders, but for some reason they've got rigid bodies. They don't absolutely need them, and they're a massive overhead in terms of calculations because the physics engine goes, I need to calculate what's happening here. And then goes, okay, nothing needs to be done. All right, so it's another gotcha that you'll just go, oh, didn't even think about that. Now you need colliders for lots of things, buttons on screen and things so you can touch them and those sorts of things. So colliders are not necessarily a bad thing, but if you don't need them, get rid of them. So if I open up the optimized one, there it is there. Don't save any of my changes. And I hit play. You'll see, so this was the detailed version, but if you look over here, you'll see a fair difference. See all that blue there? And you go over here, there's just no blue. All right? All of a sudden, those scripts are hardly using any CPU. And as I said before, you don't want to go in and just look at the details, because what ends up happening, and now I'm trying to find where the update is, because it's moved down. And I still, there it is, behavior update. And in here, and what you'll find is, every now and then you'll come across the actual frame that's where the fixed updates are happening. So you'll be able to see on fixed update what's happening as well. And that'll be obvious, because every now and then you'll have all these frames, and then bang, there'll be a very different looking frame. But if I go in here, you'll see that this is now reduced to, where is it? Where is the rotator? Did I open up the wrong level? What level am I on? Fixed update comparison many cubes. Yeah, and it's not even in there because it's just not chewing up any CPU unless I removed it. There we go. So here it is here. So here you can see 15%. Remember before, like it was around about 30%. So we've massively reduced the amount of time that that's now consuming. And so this is the situation that you want to be in, is if you're creating something that's got a lot of logic in it, or a little bit of logic in it, you always want to look at how much CPU is it consuming and can I optimize it. Some of those are going to be patterns that you can put into the parent class that you're using, and so that no matter what happens or if someone else comes into the project, immediately they benefit from all those performance gains. You'll also notice that if I just go down here, there's no physics. So we've gone from having physics happening to just no physics. All right, this wouldn't have had a massive CPU overhead, wouldn't have been that big, but it's a lot bigger than nothing. Now we have none. Right, so it's just something to bear in mind. Okay, I'm just going to go back to the slides. Sort of go through a few things. Hang on, did I press the wrong one? There we go. So some of the other things that you probably want to watch out for. So one of those is logging to console. I didn't really go through it there because it's sort of pretty boring. But if you're logging in your application, it's incredibly expensive. It's the same as logging has been for a long time. It's sort of like having debug stuff all through your code. I would only do it on error. You can inspect so much in Unity without having logging. Maybe add it and then remove it. Don't just have it sitting there forever, right? And just think that it's going to perform well. The other thing is when you go to a phone and you're running in debug mode and there's an error, all that logging will just start filling up your screen. And you get terrible performance with it. I wouldn't recommend actually to have any logging unless it's on a crash error or a critical error. Even if it's an error that can happen. If you've got an object that maybe has an error every now and then and you log it, but you've got 1,000 of those objects in memory and they all have the same error at the same time, you're just going to have this performance overhead that's happening. Logging is a bit of a hidden, so it needs to be like the app is crashing error. Yeah, otherwise you're not getting value out of it. During development time it's good, but I would just get rid of it all in your runtime code. We talked about this transform, so I'm not going to go into that much more. The next thing I'm going to talk about is sort of textures. Now, this is a very quick and easy one that I want to talk about. Textures are the images that you apply to things. So the cubes had an image on them, and that's the texture that gets applied to them. There are a lot of things to do to optimize textures. One of those is make sure it's in the right file format for the devices that you're heading to. But on any platform, you'll want your images to be base 2. They need to be 32 by 32 these days. Obviously, that's quite small. But you're looking at 512 by 512, 1024 by 1024, 4096. You can have a machine handle a 3000 by 3000 image terribly, but it could handle a 4096 just smoothly. They need to be base 2. It's the way their graphics card works. I'm not going to go into the details, but by making it base 2, you actually increase the performance. Now, if you're using Unity, Unity will resize a lot of your textures to base 2, and I see a lot of people go, no, it's this size. I don't want you to resize it and rescale it, and then they get terrible performance. Okay, just trust that Unity knows what it's doing, because it's just ridiculously important. I'll go quickly across and just show you what textures are in Unity, just so you know. If I go into Media, Textures, there's a heap of textures in here. Hang on, it's not up there yet. No. It's not switching across. Excuse me? I'll keep talking while we're working this one out. I'll go and show all this later. Collisions, I talked about this. The thing about collisions is you can assign layers to objects. So I can have buttons be on the UI layer. I can have raindrops just to be on the superficial layer. I don't want the rain to collide into raindrops or create calculations raindrop. They're just sort of for a visual cue. And explosions, I might not even have collisions with explosions, right? But I will have collisions with buildings. I will have collisions with, if it's an architecture application, I might want to collide with certain things and have collision. Collision could be used not just for interaction, but also for the camera to know where to not sit. So if you were to pan inside a building in an architecture application, you want the camera to go back to the latest wall. You don't want it to go through the wall. The thing is that with those layers, you can also say, well, you know what, the UI never collides with the landscape. So never go and calculate that. And the landscape never collides with the explosions, because I only care if the explosions collide with an individual maybe. So there's those sorts of things, and I can sort of show you that where you do that. And one of the things that I'd recommend, and I'll show you it again later, is you've got to cull those collision layers aggressively. I wouldn't go in there and go, do I need to worry about that? You should just go, the UI doesn't collide with anything else. This shouldn't collide with any of that. And then when you're using your application, find the exceptions, because maybe it only collides with one instance of that thing, and you can sort of deal with that in a separate way rather than calculating all the time. The next thing is singletons. Singletons are very powerful in Unity, but you need to be aware that you might not necessarily be in control where the application lifecycle starts. And by that is the application loads, yes, but if you're testing a level, you're probably not coming in at that same point of entrance to a game, which might load many levels. So when you're testing a level, you need access to those singletons. So how you instantiate them is important. You can come up with your own models because there's lots of ways to handle that. I'll show you a way that I work with singletons in a second. But it's very important when you start to think, well, rather than get something expensive from every object, every frame. So before I was getting the position of the object, which is relevant, but maybe I want access to, it's good, that's up, the audio manager. Excellent, thank you. And maybe I want access to the audio manager or something that's listening to audio, and I get access to the instance of that because there's only one. If I do that every frame, that actually gets expensive. So maybe in the singleton, every frame, I actually go and get access to it, and then everything else uses that instance, okay? And it might be a frame late. You might be worried about synchronization issues, but you should sort of go, okay, this is something, it doesn't matter if it's a frame late, it's still, the data is still relevant. So I'm going to go back across now to Unity. There we go. And just go back to the texture stuff that I was talking about. So here you can see I've got a texture. These are all the different textures that I pulled in. And it says here what type is it? Is it a texture? Is it a normal map, which is about having bumps on an object? A heap of different things that I'm not going to go into. Is it a sprite? And it deals with sprites a bit differently. If you're doing a 2D game, it's more of a way to manage them. So if you're doing something that's a 2D game or a 2D application, you might want to use the sprite system. And then you've got a few things down here, and the most important one though is down the bottom, the max size. So when I can actually say, hey, I only want this to be 1024 by 1024, or I actually want it to be that size. The other thing is you can do platform specific sizes. So on Windows, I want to override it and make it smaller, because maybe I know that on Windows, it can't handle 2048 on the devices I'm targeting. On iOS, it can't handle certain image sizes, or it might be the number of images that I've got on that device might change. So that's that bit. I'm just going to sort of go back through my notes. Collisions. So the collisions in a project, you go up here, project settings, physics. You've got 2D physics and 3D physics. In this, revert. Over here, you'll see these are all the different layers that I have. So these are sort of the default layers that the game will come. Your game will come with, except for background. Background I've created. There's actually a background behind everything. I've just sort of said, hey, it's a separate layer because I want to render it behind everything, and that's sort of about using cameras. But here, it turns up in the physics, and I can actually just say, you know what, the background doesn't collide with anything. And so I can go down here and go, the background does not collide with anything, so there's never been any physics calculations. So then when you have colliders associated, it doesn't matter. It'll just go, hey, it's got a collider, what does it collide with? Nothing. Okay, next. You'll still do that bit, so you want to get rid of the colliders if they're not needed. But this just ensures that we're not doing those calculations. And sometimes you get some massive performance boosts just by doing this, because you don't even realise that it's trying to figure out whether something collides with something else. And I talked about singletons. So with singletons, I'm going to also talk about audio. So I need to go into levels. And audio playback. Actually, no, I'm not going to talk about audio. My mistake. We're probably going to run short on time for that. I'm going to talk about pointer tracking. So here, and I'm going to do the optimized level because we don't need to go through optimizing it. So here I'm going to show you how you can use visuals. So here I've got the cubes, and now the cubes are actually looking at the pointer. So if I pull it out, I was going to change this to be eyeballs, by the way, but then it was too freaky. So I changed it back. So here the cubes are looking at the pointer, moving around. I can use my finger on the screen because it's a touch screen as well. And so they're just following it around. Now, one of the things you can do is every frame on every cube, you could say, hey, figure out where the arrow is in the world, where the pointer is in the world, and look at that point. The thing is that saying, hey, figure out where the pointer is in the world is a really expensive thing to do, and I'll show you what the code looks like. So I'll go into this version just so that I can find it easy. Go in here. Let's look at pointer. So this is where I was talking about colliders before. So I can actually say, hey, take the pointer and pretend from the camera to the pointer, where the point of the camera is to where that pointer is on screen, sort of both ways. Just draw a line until you hit something. And when you hit something, look at, that's the point that I want that's the point that I want the cube to look at. So the first thing is I go find that point. So I shoot, it's like shooting a laser into space until it hits something. And I've got a flat collider sitting right over the camera. So you can't see that, but it's there. And if it collides based on the mouse position, this dot transform, which we all know is poor performance, look at that point. So that's all you need to do for the cubes, right? It's just make them look at that point. So it's all built into the transform, it's built into the physics engine. But that's happening every object, every frame. We want it to happen every frame, but we don't need to calculate it for every object. So what you can do, if I open up the higher performant version, this version, on the camera, and it could be anywhere, it doesn't need to be on the camera, but the camera's always going to be there, I can open up this script. So I remove that script from all the cubes, and here, what I do is, every frame, every update frame, you'll see there at the top, I just calculate the look at point. And then I calculate it, do the same calculation, I store it in a local vector so that the other objects can get access to it. And I also store it, and that's a property, but then I store it in a reporting vector, so I can just see it in the actual editor. So if I hit play here, and look at the game world, you'll see it looking around. We're actually getting a lot of frames then, just because of the resolution. But you see it looking around. If I click on the main camera, you should see the values change. So you can see there the values are changing. And that's just so we can go, okay, cool, it looks like it's looking at the right thing. Now, what the cubes do, every frame, now, is they just go and get the instance of that singleton. So it's a singleton class, but it's a behavior that I've attached to an object. And you can go and add some other things so you don't accidentally add them to other objects because you're instantiating them on the camera. Between multiple levels, you're then going to instantiate another version of that. So you need to be careful, and there are ways to do that. I'm not going to go into that necessarily. But here, every frame, I'm not calculating it. I'm calculating it every frame, but I'm actually looking at that point. And this is where I was saying, looking at the last, what order is that happening? And I don't know what order it's happening in. And I can go and find out, and I can maybe force an order. But here, I don't really care if it's one frame behind in regards to where the mouse is, because I'm just moving my finger around. I don't care if it's a couple of pixels off. I don't know where the cubes are looking. I think they're looking at it the right way. But it's good enough for the experience. Sometimes if you need to really force that, then yes, sure, you're going to actually force the execution order. Or the first object that calls it might actually do the calculation, the rest of them don't. But you might also then, that information might be needed by everything. You might need that information by everything all the time. And that comes down to when you're doing audio. So if you're doing audio, you might go, hey, I want to get access to the audio listener and pump it out that way. So I've only got a few minutes left, so I want to sort of quickly go into audio, and I'll sort of go back to the slides. So if I talk about audio, go into levels. Here we have a level, and if I hit play, okay, so we've got some audio. Turn it down. Bit of safety dance in the background. But here you see that, we're still running the same application, but we're running some audio in the background. All of a sudden, we've introduced a massive overhead in terms of CPU. And that's really important because the audios are like one of the last things that people add, and then all of a sudden they don't realize that it's going to destroy the performance of what they're running. So a lot of it has to do with what you're doing with audio and how big your audio is. A music file is an MP3 file or an Ogg Vorbis file or compressed file is going to be playing. That means it's getting decompressed at runtime, which is going to be using up clock cycles. Or you can decompress it and have a 40 meg or 50 meg file sitting in memory. And these are decisions that you need to make based on what your scenario is. Do you need the performance or don't you? On these devices, on mobile phones, there's generally one MP3 or one audio decoding chip on the phone. So your background audio can be an MP3 and you'll have very little overhead on the chip. As soon as you introduce another MP3, that will actually be decoded by, and rather than the hardware dedicated to music, it's dedicated to everything else. So your CPU is going to start decoding it and it's going to have a massive impact. So like hardware acceleration for graphics, if you start doing it on the CPU, it's slow. Same is the case for audio. Now, the gotcha is, if you come into audio here, or in my project I've got audio here, and I've got music, you've got 3 options. And I'm not going to show you them because in the performance, in the profiler, because it does take a long time to wind them all up. But you've got a lot of options. Does it need to be mono, or does it need to be stereo? So sometimes in games, someone's shooting a gun. That gunshot audio doesn't need to be in stereo because it's going to be over there, over there, over there. You don't need to know the left and right audio noise for a gunshot. Same goes with a lot of effects. So that's the first thing, because that will reduce your file size and reduce your processing. The other thing here is you'll see, if I open it further, you can also change it per platform. So you can say, hey, I would prefer to have it compressed as MP3 or Vorbis, depending on maybe natively on those platforms, they're better at decompressing one file type or the other. If we go in here, you know, you'll be able to see where the PCM doesn't really give you a lot of compression, but it performs better than Vorbis and some of the other platforms. But what I'm going to do here is just sort of show you these 3 options: decompress on load, compress in memory, and streaming. Streaming means that it will pull it off the disk and decompress it at runtime. Compressed in memory means it will load it off the disk, but it will still decompress it as it plays. And they both have big CPU overheads. Streaming is generally the way you're going to do it, unless you think there's some sort of I/O issue with the disk. And then decompressed on load is it will just load it straight up into memory, decompress it at the beginning, and you'll end up with hardly any CPU overhead. And so, and you can see that if you just get into the profiler, you'll just see audio CPU usage is like this. You make it decompress on load, and it's just flat. My recommendation is sound effects and everything else are always decompressed on load. So that means you need to be mindful of how many audio samples you're loading, because you can end up with a gig's worth of audio in memory. And then all your audio files, like your music in the background or that ambient noise that you're going to have, you should do it as streaming or compressed in memory. And trust me, you can very, very quickly, if you're not looking at what you're doing, have gigs of audio sitting in the background. Because every time you have something that can make that sound, it will load it up ready to go. Okay, so if you have 100 objects that all can make a sound, and they're all different objects that can make a sound, and they all can make that sound, if you're allowing them to all make that sound at the same time, then it needs a lot of copies of that in memory to be able to work with it. So be very careful. It's one of those things that you just go, cool, I'll add some audio. Oh, now nothing works. Cool, I'll just go back across the slides. The next thing is draw calls. There's a concept of sprite batching. For a lot of you might be doing 2D applications, you might have overlays. Sprite batching is a way to, every image, every texture file that needs to be painted to screen gets painted one at a time. Think of it like a brush. And the thing that somebody described it to me is like Homer with the makeup gun. He sort of like packs it all in and you can actually paint something really complex in one go. It's expensive to load up the graphics card with the texture, but putting it to screen, no matter how complex the arrangement, is really cheap. So what sprite batching allows you to do with sprite sheets, so here are just some sprite sheets that I've used before. Generally, you put the things that will be drawn together, or the things that belong together, on one sprite sheet. So on the right-hand side, you've got all the UI, and there's some empty space there, but that's fine. Because at the end of the day, the UI generally is always just going to get painted, bang, there it is, done. The UI all in one go, and that sits over the top of the rest of it. If you have things sitting over the top and over the top and over the top, each time it's doing a layer, it has to do another draw call. It can't just sort of batch all of it into one draw call to paint the back and the front at the same time. It has to do them in layers, and that's a gotcha. A lot of people go, hey, I've got my sprite sheets, it's only 2 draw calls for everything, and that's not going to be the case. If you had some UI in front of some landscape, and then some landscape over the UI, and then some UI back over that landscape, you're going to end up with a lot of draw calls. The place that this usually gets people is with particles that explode. The reason you can do that, it's one draw call for the 100 particles on screen. But if you have things sitting in amongst those particles, you will actually end up with, might have 20 things that were one draw call with particles exploding on it, you're going to end up with 40 draw calls because it's going to draw all those things individually and all those particles individually. So just be mindful of that. And this will give you an example. So this is a game that I worked on called Super Conga Lion. And all the monkeys are all the animated monkey frames. There's the lion. They all overlap, but as soon as particles were happening on top of them as they ran around the screen, because it was happening within them, it was actually meaning that all the stuff that we were saving from batching all of these draws in one go was just getting totally demolished, and so therefore the devices were performing poorly. Just sort of wrapping up, because we're sort of running a little bit over. Reduce the object count. I talked about it before, but just keeping track of objects gets really expensive after a certain amount of time. And so all these objects in your level, see if you can figure out how to reduce it. The other thing is sometimes, and in the Conga game, because you can have 200 monkeys running around, what happens is just for them to go, hey, I calculate where I need to go, what do I need to do, and just to sort of do it in order, actually became quite expensive. So we created a singleton that every frame was keeping track of everything and just telling them in order what to do, and therefore the game didn't need to keep track of which it had updated and not. And we got some significant performance boost by that. So sometimes it's sort of a late optimization thing, but you just don't want a heap of objects if you don't need them. Disable unused objects. You can disable objects and re-enable them later. Shaders, I think this is probably more to talk about graphics capabilities. Be mindful that the graphics capabilities of all the devices you have vary. If you're using certain things within the graphics shaders, and when you're applying certain effects graphically, on another device might perform terribly. So just be careful what you're using. If you're going for a broad range of devices, keep it simple. File formats, I talked about this before with audios, the same with images. You can choose how the images get compressed when they get sent to the device. Images compressed in the right format are going to perform really well. Images compressed in the wrong format are not going to perform well at all. Same goes for audio. Last one is file sizes. File sizes can be oppressive. Some of those 2000 by 2048 by 2048 images, if they're not compressed, are just huge, right? Or 4,000. And so if you've got 5 or 6 of them in an app, you've got this over 100 meg app, and all it's doing is something really simple. You've got audio in there as well. You need to be really mindful of file sizes, and you might be including files that are not in there. One of the things I'm just going to show you quickly is Unity has an asset store. So think about an app store for everything for building a game or building an app. Oh, hang on. No, that was me. No. I'll work this out one day. Here we go. And this is the Unity app. So it opens up within Unity, right? And so you can go through. Here's an app that's actually written by a guy I know. It's currently featured, so that's interesting, where you can just build whole terrain and worlds just automatically out of the box. And when you look at the cost of it, which is $45 or whatever, something like that is so worth your time if you're going to build landscapes. Yeah, like it would take you years to build what this builds in minutes. But there's a heap of stuff in here. But one of the things in here is the Unity Build Report tool, which I already have. So I can actually go across here and look at everything that I've pulled from the store. And there's Build Report. So what I can do is I can download it. It's just downloading now. Thank you, Internet. And then because I've downloaded it, once it's downloaded, because I really want to show you this. I can import it. Now that package is just a heap of files. There's nothing special. Well, there's a lot special about it, but there is a heap of files. There might be some DLLs. I'll import it into my project. And this is a tool that I didn't have installed, and you'll see why, is because when I build, I go File, Build Settings, and I just go Build. I'll just build the native version. And when I build it, it's just building as per normal. But what the build report tool does is it goes and analyzes the logs and comes up with a build report. So this currently tells me the top 10 largest files that are not in my build. Okay, so that's cool because I've got stuff in my project that I'm checking in the source control, and why have I got them there? Like, why have I got these files lying around? I might have a zip file in there or a Photoshop file or whatever. And then on the left-hand side, it's saying the top 10 largest in the build. And so here are some of the files. So, Unity built-in extra, which is a DLL for some of extra capabilities of Unity. And then as you go through, you can see some of the textures are in there. But if I actually had uncompressed textures, immediately I would see it. I just go like, wow, I've got a 20 meg file sitting in there. Why do I have a 20 meg file sitting in there? The other thing I can do is I can say, hey, here's color here. It shows me it here. I'm like, yeah, that doesn't need to be 1024 by 1024. It can actually be 128 by 128. I don't really care. Like it's in the background. It's not important. So then if I go and build, I'll then see that file size will come down. So it's a really useful tool. You can do things like check out your project settings, the used assets, the things you have used. Look at all the unused assets, right? And you can go through and go, why do I have like a 13 megabyte sound file just sitting in my project? And so it helps you keep the health of your projects, but also means the things you're building, you can see where your file size is getting consumed. And just lastly, and as I said, get it from the asset store, you'll be friends for life. It's just such an amazing tool. It saves you so much heartache. The emulator won't work. So what I mean by this is, A, don't test in the emulator. If you're testing in any emulator for a Unity application, you're not testing performance. All right? You might as well just test it as a desktop application or a small application or on your phone and then go, great, that's fantastic. But don't just assume the emulator is going to be, even if it performs well, the hardware on the device is different hardware to your computer, so it may not even perform at all. The hardware acceleration might not even be happening in the emulator. Input, we showed a little bit of input. Input's not something like with an application that's blocking on your main thread. It's something that happens and you get informed about. And then you make an action based on it. So you're not going to be blocking the main thread, but be careful about how you process input, right? If you're doing it in every object, it can get very expensive. Audio, we went through that, as I said. I don't need to go through that any further. So what to do? When you're looking at that memory map, I had the memory hog in there, which is a thing that you can sort of see it chewing up memory. The memory hog wasn't a memory leak. The memory hog was just something that was just saying, hey, create a heap of strings, cool, I'm done with them. Create a heap of objects, I'm done with them. What you want to do is pull your objects at instantiation and then pull on them. Maybe you only use 50% of them or 60% of them, but you don't want to be creating objects at runtime because that creates a lot of garbage collection, and that garbage collection will actually impact the performance of your application. If you're doing something 100 times a second over 1,000 objects, 100,000 times a second, you're creating a very small object. Obviously, you end up with a few megs. Then it's sort of building up on garbage collection. Garbage collection comes along, you've got no control over when it happens, and it can really impact the experience of your application. So you're better off using more memory and keeping it flat. If that profiling tool looks dead flat, except for maybe the top one up the top, but if all those others look dead flat, you've built an application in an idyllic state. Sometimes you can't do that, but try and do it as much as possible. And what to avoid? I think we've gone through a lot of this, but bad draw calls, things where you're just drawing things with things overlapping and doing it the wrong way, not sprite batching, things like that. Creating a lot of things per frame, so sometimes you, as I said, if you're creating a lot of different little objects, even if they're only just a few bytes or even a kilobyte, a kilobyte would be dreadful, but even if you keep creating something that's 100 bytes, you will notice the impact to your application. And the thing is, using capabilities that are not in the graphics card. This is a thing that people get caught out with all the time. They're on a PC or they're on a Mac and they create something amazing in Unity and it looks beautiful. They go fantastic and they ship it and they try it on this device and another device, and you know what? They're the only two cards that support the graphics feature. And all of a sudden, something that is happening incredibly fast is actually going to run incredibly slow. And with that, thank you guys. Remember, complete your session evaluations. We appreciate your feedback, and I appreciate your feedback, so make sure you do those. And the other one is continue on your Ignite learning path. Remember that there's so much stuff happening. All the sessions will be on Channel 9. There's a learning zone upstairs. There's a lot of UWP sessions coming up. Nick Randolph's bare metal one, which is happening on day 3, which is Thursdays, I really recommend going to because it's going to be a very deep dive into UWP. And yeah, thank you very much. We are running over.